In the previous video, we've seen that if the game has no saddle point, then our optimal solution is playing randomized strategies, which means that we are not going to just stick to one optimal strategy all the time, but rather our optimal strategies is with this much probability we are going to play this, and with that much probability we are going to play that strategy. Okay, so that's about randomized strategies. Now here I'm still going to talk about the game that has no saddle point, but we are going to see another concept which is called domination. Let's see an example. In this game, a fair coin is tossed and the result is shown to player 1. Player 1 must then decide whether to pass or bet. If player 1 passes, then he must pay player 2 directly. So player 1 pass and then he just loses the game and just pay player 2 $1. If player 1 bets, then player 2, who does not know the result of the coin toss, may either fold or call the bet. If player 2 folds, then she directly pays player 1 $1 and player 2 just lost because she says she's going to fold. If player 2 calls, then the result of the coin toss matters. If player 2 calls and the coin comes up heads, then she pays player 1 $2. If player 2 calls and the coin comes up tails, then player 1 must pay her $2. So I will give you a pause on this video to give you the time to really read this example carefully. I will return after the pause. In this example, we are asked to graphically determine the value of the game and each player's optimal strategy. Before going there, we need to see what kind of strategies are available for each player. Let me start with player 2 because it's more straightforward, right? Player 2 has the strategy of fold or call. So those are the only possible strategies for player 2, right? For player 1, it's a bit complicated because player 1's strategies is pass or bet, but it is also depending upon the result of the coin toss, right? Because you may think of this. If the coins looks like this, maybe you have the strategy to pass. If the coins looks like that, you have the strategy to bet. So it's really the combination between the result of the coin toss and the option of pass or bet. So because for each result of coin toss, you have two options. If head appears, you may pass or bet. If tail appears, you may pass or bet. Same here, so we have four combinations. Pass, pass means that if head appears, you pass. If tail appears, you also pass. Pass, bet, bet, pass, or bet, bet. So BP, bet, pass, it means that if you see the coin shows up head, you will bet. If you see that the coin shows up tail, you will pass. Once we have defined the possible strategies for both players, we are going to construct the reward matrix. Because the player 1 or the role player has four possible strategies, PP, PB, BP, and BB, and then the second player has two strategies, call and fold, our reward matrix has the size of 4 by 2. Because row has four strategies, column has two strategies. Okay, and then notice here that the element inside the reward matrix must show the expected reward for player 1. Okay, because the value inside the reward matrix always shows the reward with respect to the role player. So we need to calculate the expected reward for each pair of the strategies that player 1 plays and player 2 plays. For example, let me show you how we may compute the expected reward for this pair of strategies. BP for player 1 versus call for player 2. Let's start by computing the expected reward by realizing that we cannot control the outcome of the coin toss. The coin toss may comes up head, it may comes up tail. If the coin toss comes up head, then we have a certain types of reward. If the coin comes up tail, we also have a certain kind of reward. Now the probability of the coin comes up head is a half, so this is this half that you see here, and then this another half is the probability that the coin comes up tail. Okay, so we need to put these probabilities first. Now let's see what happens when the coin comes up heads using this pair of strategies. The coin comes up head, the first player bets. The first player bets, the second player calls. So the second player calls, the coin comes up heads. It means that the second player pays the first player $2. And that's why you see number 2 here. It means the role player or player 1 wins $2. Now, if the coin comes up tail, it means that the first player's strategy is pass if the coin comes up tail. So the first player pass, then the second player doesn't have to do anything. The first player must immediately pay player 2 by $1. That's why you see the number -1 here, because if the first player passes, then he must pay the second player with $1, regardless of whatever player 2 does. Okay, so the expected reward for this pair of strategies, BP versus call, is $0.50 for player 1. In other words, in this scenario, BP for player 1 and player 2 plays the strategy call. Player 1 may expect the reward of $0.50. So once we have completed the reward matrix, for example, this is the one that we calculated in the previous slide, BP versus call. Now we can see that this game has no saddle point. Furthermore, I would like you to notice that some strategies are dominated by the others. So I'm introducing the concept of domination. For example, this strategy PP for the role player is dominated by BB, for example. Why? Because whatever the column player does, this strategy PP always causes the role player to lose $1. While if the role player plays BB, at least here, if the player 2 plays call, it gets $0. If the player 2 plays fold, the player 1 plays $1. In any situation, the value expected reward for BB is always better than PP. That's why PP, we can say PP is dominated by BB. We may eliminate this rule. Similarly, you can say PB is dominated by BB because in whatever condition, BB is always better than PB, right? 0 is better than -3/2, 1 is better than 0. So if any strategy is dominated by any other strategy in this matrix with respect to a particular player, then we can just eliminate the strategy. Now, after eliminating the dominated strategy, this is our final reward matrix. You can see that no strategy is dominated by the other. For example, BP and BB for player 1. For player 1, this is better if player 2 plays core, but BB is better if player 2 plays fold. Again, for the same for column player, there is no dominated strategy because if player 1 plays BP, then this one is better. But if if player 1 plays BP, then fold is better for column player. But if player 1 plays BB, then this is better for player 2. So you can see that there is something that is better than the other with respect to the strategy of player 1. So there is no more dominated strategies, both for row players and column players. Okay, so we have eliminated the dominated strategies, and we have also realized that this game has no saddle points, which means that to find the optimal solution of this game, we need the randomized strategies. So we define the randomized strategies like this. X1 is the probability that player 1 will play the strategy BP, and X2 is the probability that player 1 will play the strategy BB, and X2 equals 1 minus X1. For player 2, we define the variable Y1 to be the probability that player 2 chooses core, and Y2 is the probability player 2 chooses fold. Now let's calculate the expected probability from the point of view of player 1 reward. So again, when we are at the position of the row player, we cannot control what strategy that player 2 will play, right? Because we cannot control player 2 in the calculation of expected reward, we need to separate the points. The first is if the column player plays core, and then the second point is if the column player plays fold. If the column player plays core, then the reward for player 1 is half times x1 plus 0 times x2. And x2 is 1 minus 1. 1 minus x1, I mean. If player 2 plays fold, then the reward for the first player is 0 times x1 plus 1 times x2. 1 times x2, and this is x2 because x2 equals 1 minus x1. And then, as usual, we may draw this two equations. With the y-axis is the expected reward to player 1. So 1 minus x1 is this one, player 2 picks fold, the second equation. This is the first equation, player 2 picks core. And then because remember, the player 2 will always try to minimize the reward for player 1. So the lines that will happen is this, from A, E to D, because player 2 will always try to minimize the reward for player 1. So the best thing that player 1 can do to maximize his profit is at this point, E. So at that point, x1 equals 2/3, and the expected reward if player 1 plays this randomized strategy is 1/3. So x1 equals 2/3 is the optimal solution for the row player. Now we are going to take a look at this game from column player's point of view. But because the reward matrix shows the reward for row player, we're still going to calculate this with respect to rows expected reward. Okay, when we are the column player, we cannot control what the row player will play. So we separate again, if row player plays BP, if row player plays BB. If row player plays BP, then the expected reward for row player is half times y1 plus 0 times y2, and y2 is 1 minus y1. Okay, so this is the row player's reward if he plays the strategy BP, and with respect to the strategies of column player. Therefore, you can see this is the expected reward for the row, but the variables is about the probability of player 2's strategies. If row player plays BB, then his expected reward is 0 times y1 plus 1 times y2, and y2 equals 1 minus y1. Again, we draw these equations with the y-axis expected reward for player 1, but then the x-axis is the probability that player 2 chooses the first strategy. And then we can see that here we have player 1 picks BB. This is the line, the second line, and then this is the first equation. And then because this is with respect to the reward for player 1 will try to maximize his reward. So the lines that will happen is from C to E and then E to B. So the best thing that column players can do, remember that column players has the control for this x-axis. The best that column player can do is to minimize the reward for row player, which happens at this point E here. So to minimize the expected reward for row player, the best that column player may do is to play y1 equals 2/3. If y1 equals 2/3, then the expected reward for player 2 is 1/3. So we have solved the randomized strategies for both row and column players. So the optimal solution says x1 equals 2/3, and then x1 equals 2/3 here, and then y1 also equals 2/3, and that's the optimal randomized strategies for both players. Now the questions are, what is the value of this game? And second, how to implement this solution in practice? I mean, x1 equals 2/3. If you are the player 1, then how can you implement that? 2/3 of the time you will choose the strategy BP. I will give you the pause on the video to give you the time to think about these questions. I will give you the answer after the pause. So the value of this game is 1/3. Because if both player plays the optimal randomized strategy, which means x1 equals 2/3 and y1 equals 2/3, it means that at that situation, the expected reward for player 1 is 1/3. Whoever deviates from that optimal randomized strategy will suffer. So for example, if player 1 plays x1 too small, then his expected reward will be smaller than 1/3. If x1 is too large, then his expected reward will also go lower than 1/3. Similarly, if players 2 plays with smaller y1 here, then it is a loss for player 2 because player 1 now may get a higher reward than 1/3. Similarly, if player 2 decide to place higher y1, then player 1 may get a higher reward as well. So again, the situation becomes worse for the column player or player 2. So the value of this game is 1/3. And then how to implement this solution in practice? Well, let's say if you are player 1 and then the optimal solution says that you should play the strategy BP 2/3 of the time. What you can do is that for each game you play, you will throw or generate a random number. That's why this is called a randomized strategy. So you throw a random number and see if the number is less than 2/3, you will play the strategy BP. But if the random number is greater than 2/3, then you select the second strategy. Same thing for player 2. If you're the column player, then you just throw a random number. If it is smaller than 2/3, you say you're going to play call in this game. And then if it is greater than 2/3, then you say that in this particular game, you're going to play the fold strategy. Okay, so that's about the domination and also about the randomized strategies. Next week, I'm going to talk about finding the optimal solution for the randomized strategies when we have more than 2 variables. We're going to use linear programming. So anyway, that's the end for this week, and see you on the next one. Thank you.